Okay, good afternoon, everybody. So, kumusta ang inyong weekend? So, I hope you had fun or you had time to relax. Kumusta ang lab exercise? Part A ng exercise 1.1. Any comments, violent reactions, or reklamo about the laboratory exercise? Just keep in mind that is a shortened laboratory exercise because we were not able to cover in the lecture last week the entire coverage of the exercise. So medyo nabawasan yun sa exercise. So the consequences, probably our next exercise will be a little bit longer depending on what we will finish today. Kasi may utang pa tayo from Lab Exer 1.1. Meron pang dalawang items yata na natitira. I talked to my laboratory class last Monday. Tapos ang suggestion nila or ang napagkasunduan namin is hindi ko na i-require na i-submit niyo siya ng mas maaga. Isasabay na lang natin siya on whatever what will be due on Monday. So posible na dalawang exercise yung ipapasa niyo on Monday. Laboratory exercise 1.1B, all right? So yun yung natitirang items. Tapos may isa pa, probably parts of laboratory exercise 1.2. Depende dun sa matatapos natin. But to facilitate the orderly grading of these exercises, I will request you guys to submit two separate files. Isa para sa 1.1B at saka isa para sa 1.2A. All right? So I hope that is clear. Kumusta naman yung exercise? Masyado bang mahaba? Masyadong maikse? Masyadong madali? Mahirap? Or saan kayo pinaka nahirapan? So guys, this is your time to share para if ever I'll need to adjust succeeding exercises, I can do so and I'll have an idea how to do it. Bahala kayo. Pagka hindi kayo nagsalita, i-assume ko na masyadong madali for you guys yung exercise. Oh yes, go ahead, Michael.
Siguro po yung isa sa mga na-encounter ko po na difficulties dun sa Excel po ay yung sa pag-graph. Kasi po ay, ang tawag dito, sobrang laki po kasi nung value so hindi po ma-capture yung buong graph.
Mm-hmm. All right, sorry na naputol ako doon, pero I hope I'm back. I think I got what Michael is saying na yung iba nahirapan dun at least some students in my lab classes, I already graded their work. So yung mga taga D2L, check niyo yung sa Canvas. I already graded your lab exer. So medyo hindi nakikita yung access kasi malalaki nga yung values. So there are softwares na ang ginagawa nila ay equal scaling. Kung gaano kalaki yung 1 unit sa x-axis, ganun din kalaki yung 1 unit sa y-axis. And that's what made the graph for the particular function we considered in the laboratory exercise a little bit difficult to display in a nice window. So what you can do is to play with the axis. So hanapin niyo yung option dun sa graphing software nyo. Baka pwedeng hindi parehas yung scaling ng x at saka y-axis. Para, halimbawa, maging itsura niya ay 0.001, 0.002. So this is 10 to the minus 3 units along the x-axis. Baka naman pwede yung nasa y-axis ay 10,000, 1,000, 2,000, 3,000, and so on para makita natin yung contour ng graph. So para makita natin siya na may curve or makita natin yung key characteristics niya. Because if the graph will be cut off in a particular frame or in a particular window, ang nakita ko lang dun sa iba, ganito lang. Parang straight lines lang na ganyan. Which is fine for our purpose because we still see the crossing on the x-axis, all right? Nakita natin yung x-intercept. So sa atin, medyo okay yon kasi ang hinahanap lang naman natin ay existence ng root on a particular interval. But there would be times that it would be better to see the contour of the graph. And presentation-wise, I think it would be more insightful to get a clear picture of the general contour or the general curve or general behavior of the graph. And I think most of you noticed this na, okay, sir, wala po akong magawa, sinubmit ko to. Pero may mga nagtanong kung ano yung mga pwedeng gawin. Some zoomed in para ipakita talaga na may crossing sa x-axis. That's fine. Pero yun nga, instinctively, alam ng iba na dapat may mas magandang presentation yung graph. So the scaling for us doesn't matter, the x-axis or the y-axis, okay lang yun. Another trick that you can do is, ang i-plot nyo ay tens of thousands halimbawa. So kung hindi nyo kayang paglaruan yung scaling, by default talaga yung inyong graphing software ay equal dapat yung scaling sa x at saka sa y-axis. Pwedeng mano-mano yung palitan yung data. Halimbawa, yung sa x-axis instead na 0.001, gawin nyo itong 1, 2, kunwari ganun, tapos times 10 to the negative 3 na lang. So you can take the logarithm base 10, tapos makikita nyo ano dapat yung, hindi pala exponent ang ibibigay nun, no? I-divide nyo by 10 to the minus 3 or ito naman yung i-divide nyo by 1,000 para yung scaling nila magtugma. Alright? So depende dun sa graphing software, no? Some people are asking what's the graphing software I'm using. I'm using Mathematica. So kaya lang walang license ng university for Mathematica. Don't try buying it. I think it's 50,000 a year. So it's not advisable to buy Mathematica. Ang ginagamit kong Mathematica is software ko pa from my previous university. So hopefully hindi nila bawiin yung license sa akin. Pero yun. In MATLAB, you can also do this by, I think, using a logarithmic scale. So search nyo lang sa MATLAB help or sa Google, paano gawing logarithmic scale yung y-axis halimbawa or yung x-axis para naka times 10 to the whatever power yung scale ng isang axis. So magiging ano siya, 1, 2, 3, tapos ang scale niya ay ito ay 10 to the 1, 10 squared, 10 cubed, and so on. So logarithmic yung magiging scaling nung y-axis kung masyadong malaking discrepancy. Okay? Another comment I have with the laboratory exercise ay yung iba nagre-rely din sa presentation nila ng data. Okay? Now, if I will be reading your submission, I might not I might not pay too much attention to the graphs or the figures unless it is absolutely necessary or if that is the highlight of the exercise. Actually, the highlight of the exercise will be on how you answer the questions, all right? Kasi wala naman sinabi ron na include a screenshot of your iterations and so on. So what I was looking for is dun sa statement nyo, dun sa narrative, dun sa answer nyo, dun sa bawat question, ay nandun dapat lahat ng detalye na hinahanap nung problem. So for instance, in the last item, I was asking for what's your R star using the function value-based halting criteria, and how many iterations was needed to get that approximate. Some of you forgot to write how many iterations, pero sa problem naka-explicitly state na sabihin kung ilang iterations. I understand some of you might have overlooked it kasi naglagay kayo ng screenshot ng iterations, nandun naman kung ilan. Pero if I am a reader that is reading your paper diagonally, I might not be paying too much attention to the iterations if that is not what I'm looking for. And unfortunately, in the last exercise, I was not looking for that in the question. So hindi ako masyadong nag-pay attention doon. Ginamit ko lang siya para ma-validate na nag-program talaga kayo or nag-excel talaga kayo. Tapos kinopya nyo yung sagot at hindi galing sa classmate nyo yung sagot. Alright? So, yun. Kaya na-minusan yung iba. So, that lesson learned, pakisagutan ng masinsinan or basahin ng masinsinan yung question and make sure that you answer everything. Okay? Now, before I was cut off earlier, I saw some other people aside from Michael raising their hand. Do you guys want to add something? Okay, may tanong si Jeanette. Pwede bang gawing 2 attempts yung pagpapasa? Sige, pwede yon. Pero ang usapan, ang check-kan lang namin ay yung pinakahuling submission. Alright? So we will ignore the earlier submissions. Kaya lang maging problematic yon sa D2L kasi pag may na-receive ako, chinechekan ko kagad. So sige, after the deadline na nga lang ako mag-check. Alright, so that's fine. Thank you, Jeanette, for the suggestion. David?
Sir, nahirapan lang po talaga ako doon sa pag-figure out on how to code the program po. I was switching between MATLAB tsaka Python kasi both po ako hindi familiar dun on how to code yung mga hindi na linear equations po. Hindi na siya simpleng polynomial na this raised to this
I
plus
see.
that. Pero
Alright.
nagawa naman po.
Okay, good. Tapos David, i-keep mo yung program mo kasi gagamitin uli natin yun sa Regula Falsi. Alright.
po,
Modify nyo
sir.
lang siya ng konti. Okay. Now that's one thing. Unfortunately, again, I think I don't remember if I mentioned it in the lecture. Pero kasi hindi programming course yung 175, so I cannot allot time for reviewing how to code. Siguro sa laboratory classes kasi 4 hours naman yon. So probably we can devote some of the time sa laboratory to help you coding or the basic of coding para matulungan kayo in the next few exercises. Siguro in in the laboratory classes in 2 or 3 weeks from now, we can add additional program to it or additional agenda in the classes to include the review of programming languages para matulungan din namin kayo. And actually, I think that's the purpose of laboratory classes. So you can please attend the laboratory classes, especially if you're having troubles programming, because then we can focus on you. Sa lecture kasi ang focus ko talaga ay yung methods lamang. All right? Any other concerns? Let me check the chat. Okay. All right. So other concerns? So if there are none, so let's proceed. Oh, by the way, I'll be posting the answer key probably on Friday. Okay. Antayin ko lang kung meron pang hindi nakapagpasa. But when I see in Canvas that everybody submitted their work, pwede ko siyang i-upload ng mas maaga. Okay. Disclaimer pala, dun sa answer key, I'll have the suggested pointing system. The instructors reserve the right to grade it according to their own judgment. So guide lamang yung pointing system doon. So your lab instructors might deviate a little bit from the grading scheme or the suggested rubric for the exercise. Okay. So medyo dumadaldal na naman ako, so kailangan ko ng dalian talaga para matapos natin yung Regula Falsi today. So pwede nyo nang masimulan yung laboratory exercise part B ng 1.1. Okay. Now, in the bisection method, again, the idea there is to start with an interval. Kaya ang tawag sa kanya interval or bracketing method. Kasi crucial yung pagpili ng interval. So we are picking an interval such that f of A and f of B, their endpoints, have different signs, or the function values at the endpoints have different signs. Because by then, the intermediate value theorem can guarantee that there is a root between A and B. So yun yung idea. So interval AB, magkaiba yung sign dun sa function values ng magkabilang endpoints. And then what we'll do is to take half of that interval, take the midpoint, and then pipili tayo dun sa dalawang kalahati o dun sa dalawang halves ng interval na yon to be our next interval. I think that's the main reason why it is called an interval method. Kasi at every step of the iteration, we are getting another interval. An interval in the bisection method which is half the length of the original interval. Tapos ang pinipili nating estimate para dun sa root ay yung midpoint, which is C equals A plus B over 2. And then we go to the next iteration by picking the next interval. So we're picking the next interval so that one of its endpoints would be the value of C. Yung midpoint from the previous iterate, siya yung isa sa mga endpoints. And then we're picking the other endpoint of the new interval to be one between the previous two. It's either the old A or the old B. Ang criteria, piliin mo sino yung may kakaibang sign kaysa kay f of C para sa susunod na iteration, you're back satisfying the original condition that the endpoints of your interval will have opposite signs. Okay? So hopefully you already figured out a nice way of writing that into a code. Kasi ngayon, mag-introduce tayo ng ng isang bagong method which has a very similar approach as the bisection method. Pero kakaiba ngayon yung pagko-compute niya ng C. Okay? Hindi na basta midpoint. Meron na tayong criterion na gagamitin. Okay? Now, ano yung problema sa bisection method? Lagi nga siya nagko-converge dun sa root. It's always guaranteed, but the convergence is spectacularly slow. Nakita natin ang ang rate of convergence ng bisection method ay linear. All right? The asymptotic error constant is 1/2, meaning at every step of the way, the error or the estimate for the error is half of the previous estimate for the error. And the order of convergence is big O of 1 over 2 to the power n, meaning the error or our sequence of approximates converges to the actual value as fast as how 1 over 2 to the power n approaches 0. Okay? So usually gusto natin siyang pabilisin. And then one possible way to speed up the process is to use the Regula Falsi Method or the method of false position. Okay? So ang idea ng Regula Falsi ay ganito yung idea, geometrically. Pag meron kang isang curve, okay, clearly isa yung curve. If you zoom in to a very small part of this curve, all right? Meron kang curve along the xy axis. Kung titingin ka lang sa isang maliit na interval, okay? Palakihin mo yan. And look at this. If you will zoom in enough, kaya lang hindi na kaya ng notability na i-zoom in, para siyang nagiging isang straight line na lang. So if you have a very curvy graph, okay? Nakakurbada talaga siya. Pero mag-zoom in ka sa isang maliit niyang part, it will always look like a straight line. So parang saan lang yan? Parang kung bakit may mga flat earthers, alright? So dahil may curvature man ang Earth, okay? Pero dahil nakikita lang natin yung napakaliit na portion ng Earth, akala natin linear na yung behavior niya, or we might be led to believe that that we have a straight line, or there is a straight edge for Earth, right? Where in actuality, siya talaga isang curvature. Okay? So yun yung idea. So the idea is, dun sa interval na kino-consider natin sa bawat step of the way, we will approximate the curve by a line. Halimbawa, nasa interval, nandito ka sa interval AB. Okay? Ito yung f of A. Iba yung sign niya sa f of B. Okay. Alright? Yun din yung condition. As I mentioned last time, parehas lang yung condition sa bisection at saka sa Regula Falsi, right? Dapat magkaiba sa yung sign ni f of A at ni f of B, thus IVT guarantees the existence of a root. Now, the method works this way. Gagawin ko ay i-approximate ko yung curve over the interval AB by the line passing through f of A and f of B. I-assume ko linear yung function over the interval. So, i-approximate ko siya by a straight line. Okay, walang ko-contrast, straight line yung orange na yan. And then our first estimate, since we are replacing the pink function here by the orange one, okay, ito yung approximation natin. Our first estimate or our estimate for the root would be the x-intercept of the straight line. So ito ngayon, yung magiging value ko ng C. Alright? So this would be my C, right? Or my C1. This is my first estimate, okay? And then, if the stopping criterion or if the stopping criterion is not yet met, then I will repeat the process over and over again. But this time, I will consider a smaller interval. And that interval should include C as one of the endpoints, all right? Tapos yung kabilang endpoint, pipiliin ko to be one of the previous endpoints which will possess the opposite sign kesa dun sa f of C. All right? So, eto si C, ayan yung estimate nating bago. Yung f of C ay nandito. Right? And f of C is negative. Ang usapan, katulad dun sa bisection, yung function, yung estimate natin ngayon, dapat maging endpoint yan dun sa susunod na iteration. Paano mo siya pipilian? Dapat yung function value ni C ay opposite ang sign dun sa napili mong isa pang endpoint. So we will be choosing between A and B, but this time, since f of C is negative in my example, I'm gonna choose B to be the other endpoint. Okay? So dun sa susunod kong interval, sa susunod kong iteration, eto na yung bago kong interval. So this would be my new A. Tapos, eto pa rin si B. Eto pa rin si B. So we are now in a shorter interval, but you see here, graphically, na hindi na siya katulad ng bisection na kalahati lagi nung length ng previous interval, yung length ng current interval. Kasi nga, nakadepende dun sa x-intercept nung line passing through the endpoints, all right, of the original interval, yung nagiging estimate natin. Pero yung idea, i-keep mo si C as one of the endpoints of the new interval and choose the other interval to be one among those or one between the previous two endpoints that will have an opposite sign with f of c. All right? So in this case, si f of b yung napili ko. Tapos ulitin ko lang yung process hanggang hindi ko pa nasa-satisfy either yung interval-based stopping criterion or yung function value-based stopping criterion. So yung next iteration niya, ganito yung magiging itsura. So I'll use a green one. So kukunin ko ulit yung line passing through the two endpoints. Okay. And then the false position ay ito. Ito yung false position ng root. So this would be my next estimate for the root. All right. And you see, I am now getting closer to the actual root. Because on this interval, kasi mas maliit na yung interval, mas linear na yung behavior ng function. So yung linear approximation para dun sa curve ay nagiging malapit na dun sa actual curve. All right? So this is my new estimate, and I'll check, do I satisfy the stopping criterion already? If not, then gagawin ko ulit yung ulitin ko yung proseso. All right? So I'll look at f of c. My f of c is here. It has a negative sign, all right? So dun sa susunod na iteration, ikikeep ko si C as my endpoint. Tapos pipiliin ko na naman which among my current A and my current B will have a function value that is opposite to f of C, or which will have an opposite sign to f of C. Ang f of C ay negative, yung f of B ko ay positive. So i-retain ko si B as my B, tapos si C, siya na yung magiging bagong A. Ito na yung magiging A dun sa susunod na iteration. Okay? And then, you'll continue the process. Okay? Tapos ito yung idea graphically. And again, the main point here is that yung pinaka-basis ng Regula Falsi is if you zoom in into a curve enough. So if you will zoom in enough, you will see that the curve will behave almost as if it is a straight line. Okay, that's why the x-intercept of the straight line passing through a f of a and b f of b will be a good estimate to the root of the function. Okay, so any questions? So ito na, yung Regula Falsi method. Napaka-simple, di ba? So again, it is hinged on the linear approximation of the curve over a small interval. Okay, of course, if your interval is long, okay, posibleng hindi maganda yung linear approximation dun sa curve. Kasi nga nag-work lang tong approximation na to pag napakaliit na ng interval. But if you will repeat the iteration a lot of times, thousands of times in some examples, then you will be guaranteed that you will get a good approximation. And the nice thing about the Regula Falsi method is that it satisfies it also possesses the same nice characteristic as the bisection method. Guaranteed lagi na magko-converge yung Regula Falsi method. So it might take you a while, but the good thing is at the end of the tunnel, after performing all these iterations, makakarating ka dun sa root because the sequence of approximates obtained using the Regula Falsi method will always converge to a root of the function. Okay? So wala tayong problema, no question about the convergence. But we will see later what are the issues that are inherent or that are present in the Regula Falsi method. Okay? So yun, do you have any questions about the idea of the method? Kaya nyo na bang ikwento? Kasi baka sa problem set, ipakwento ko sa inyo yung Regula Falsi. Alright? So I hope you can do it. Let me see some reactions kung okay ba yung discussion nun. So yun lang talaga yung Regula Falsi method. You might say na naunahan lang tayo na nag-invento ng Regula Falsi method because it's very simple and it has a nice and intuitive foundation. Okay, no questions? Okay, nagigets daw ni David pero hindi pa niya tanggap. All right. But you will see it when you implement the method. But I hope the graphical explanation is clear. So ganun yung nagiging idea. So yeah. So alam na natin yung graphical sense ng method. Tingnan natin kung paano natin siya i-implement. How is it done analytically? Now, it is also simple kasi nga meron tayong we start with an interval a comma b such that f of a times f of b have opposite signs. All right. Tapos sabi natin, kunin natin yung, ginagamit natin yung x-intercept ng line passing through the endpoints. So kunin natin yung equation of the line passing through the two endpoints, right? Remember your points, your two-point form of a line. Meron kang y minus y1 equals y1 minus y2 over x1 minus x2 times x minus x1, all right? So sa elementary algebra nyo, ito yung equation ng line passing through the points x1, y1 and x2, y2. So we'll just apply this this formula para makuha yung equation nung orange o kaya nung green line dito. Or kung ayaw nyo na, nakalimutan nyo na yan, pwede nyo gamitin yung Lagrange form ng interpolating polynomial. Gamitin nyo itong dalawang points na to. So, i-run nyo yung program nyo from 174. Makukuha nyo yung equation nung line passing through those endpoints. Alright? But it's quite simple. Tingnan ko lang kung paano ko siya dinerive. B yung ginamit ko. So, yeah, the equation of the line will be y minus f of b equals f of b minus f of a over b minus a. So remember, this is the slope of your line times x minus b. Kasi f of b yung ginamit ko rito, so b ito dapat. Okay, so yan yung equation ng line na daraan dun sa endpoints. Tapos, gusto natin kunin yung x-intercept. Do you guys remember how to compute for the x-intercept of a line? Paano natin kinocompute si C? Come on, guys. Or masyado bang basic yung question? Sayang yung bonus points. So, paano ko makakompute si C? Alam ko na yung equation. So, anong kailangan kong gawin dito para makuha ko yung value ni C? Yes, David?
Sir, set po yung value ng y sa 0.
Okay, great. So, we are looking for the value of x such that y is equal to 0. Para makuha si C, okay, kunin natin yung value ni x na nagzi-0 yung y. So here, let's just let y be equal to 0 to get the y-intercept and then solve for x. So we'll have 0 minus f of b equals same thing, okay, times x minus b. Then let's solve for x, all right? Solving for x will give us what? We'll get x, all right, equals what? X equals negative f of b times b minus a all over f of b minus f of a, tapos magkaka-plus b ako. Tama ba? Sana tama yung algebra ko. So double check the algebra. So I just let y be equal to 0 and then solve for x. Tapos, ito yung magiging value ni C. So dun sa bisection method program nyo, si C ay equal sa a plus b over 2. Tama? So sa Regula Falsi, papalitan nyo siya. Yung C, ito yung value nung C na gagamitin nyo. Okay? But the entire machinery that you built for the bisection method will still work for the Regula Falsi method. Okay? So, and then, yeah, i-rerun nyo lang siya na bago lang talaga yung value ni C. Alright? And I guess in the module, I have the exact derivation over here. So the value of C actually is in equation 2.9. Ito yung pag-compute natin sa value ni C. Okay? So is everything good? Kaya pala natin i-discuss yung bisection method ng isang page lang, no? Yung Regula Falsi. Tapos sinype ko pa siya sa latex ng napakatagal. But anyway, hindi ko kasi alam kung okay sa inyo yung mga handwritten notes eh. Kasi pwedeng gawin natin na on the spot lecture na lang. Susulat ako, pero kailangan kong gandahan yung sulat ko. So, but anyway, so that's the method. As simple as that. Okay. Now in figure 2.5, I have here the same similar illustration as what we had. Okay. And then it would be a nice exercise if you can write a step-by-step procedure for the algorithm. You can pattern your answer in exercise 2.4 dun sa ginawa ko for the bisection method. I think I listed down the recipe for the bisection method. You can pattern your work for the Regula Falsi to that step-by-step recipe. Okay? Now, let's look at some quick examples. So, remember this function? Ito yung function na napakaraming or na may infinitely many solutions. All right? Kaya lang dito titingnan natin yung yung solution over specific intervals. All right? So, siguro tingnan natin uli yung graph ng function. Nasa figure 2.3 raw. Hindi pala gumagana yung link, yung hyperlinks dito sa annotator ko. Pero sa PDF reader, if you click on this guy dun sa figure, i-direct kayo dun sa figure 2.3. Pero dito, kailangan ko pala siyang gawing mano-mano. Okay. Saan na tayo? Figure 2.3. Okay. This is the graph of the function we will examine in the example. So you will see that there are lots of roots over the real number line. Okay. Kaya lang alam natin positive na lahat ng roots kasi nga na-analyze natin ito dati na walang negative roots kasi nga yung e to the minus x when x is negative is much larger than sine pi x over 2. So hindi posibleng mag-negative, imposible na mag-0 for negative x's. Okay? So i-examine natin yung mangyari over specific intervals. I think we'll be looking for the roots over the interval 0, 1 and the interval 1, 2, if I'm not mistaken. So yun yung mga i-consider nating interval doon. 0, 1 at saka 1, 2. Okay? So sa dalawang intervals na yan, maghahanap tayo ng roots. Iraran natin yung Regula Falsi Method. And you will see some subtle differences in the results of the Regula Falsi Method over these two intervals. Ito yung kaibahan niya. Yung Bisection Method kasi napaka-uniform ng process, right? It doesn't matter how your graph looks like or how crazy the oscillations are. At every step of the way, kinakalahati lang natin lagay yung interval, right? But that's not the case for the Regula Falsi Method because the length of the next interval or in the next iteration of the method is dependent on the behavior of your graph, all right, or the behavior of the function over the current interval, okay? Hindi natin na-predict gaano na kaiksi yung magiging susunod na interval. So computing for the asymptotic error constant and consequently the rate of convergence is quite difficult to do or to analyze in a general scenario for the Regula Falsi Method. Wala tayong magagawang analysis na katulad nung nagawa natin sa Bisection Method. Okay? So let's go back to the example. Okay. So iraran natin siya sa interval 1, 2. Tapos ang gagamitin natin ay interval-based tolerance na 10 to the minus 6. Okay. Now, I implemented it in MATLAB. Ito yung nakuha ko. All right. So it looks like that after 10 iterations, I got the root on the interval 1, 2. And this is a good one because it only took 10 iterations to satisfy the interval-based criterion. Okay. And the function value is 10 to the minus 16 or is of order 10 to the minus 16. So that is good enough. When I plug in 1.94893 to the function f, ito yung ibibigay niya sa aking function value. So since the function value of my estimate is close to 0, then I can say that my estimate is a good one. Malapit sa 0 yung function value niya. So it is close to being a root, okay? And also, since we use the interval method or the interval-based stopping criterion, we know that this is within 10 to the minus 6 units away from the actual root. Okay? So kasi nga, yung epsilon natin ginamit, interval-based, ay 10 to the minus 6. So alam natin, ang layo nung estimate ko na R star ay 10 to the minus 6 from the actual solution. And it is not surprising to get a function value that is very small for R star, even though we are interested in the distance between the actual root and our estimate kasi interval-based yung ginamit ko dahil wala namang malaking oscillations yung nangyayari dun sa function. Same lang yung scale ng x at saka y axis. So a small change in the x value translates to also a small change in the y value. So konti lang yung pagbabago in terms of absolute absolute differences. So kaya kaya ganun kaganda yung function value ni R star. Hindi katulad dun sa example niyo sa dun sa exercise na ginawa nyo, na yung maliit na change sa x value, napakalaki ng change sa y value kasi nga magkaiba yung scale. Gumalaw ka lang ng order 10 to the minus 3 sa x-axis, pwedeng mag-jump ng order 10 to the 1 or 10 squared dun sa y-axis. So, kasi nga, magkaiba yung scaling. Pero dito okay lang. So, maganda yung nakuha nating estimate. And it didn't take too long. It's just 10 iterations. Kaya lang, tingnan natin yung example 2.5. Same function. Okay? Though a different interval. I'm now on the interval 0, 1. Tapos same tolerance, 10 to the minus 6 din, yung interval-based tolerance na gagamitin ko. But this time, I will impose also that the number of iterations will not exceed 100. Okay? Tapos yung result niya, nasa figure 2.7. Okay? And you will see here that after 100 iterations, yung length ng interval na kung nasan ako ay 0.443574. Okay? Hindi siya ganun nababawasan. And this is one of the drawbacks of the Regula Falsi Method. Kasi hindi natin nagagaranti na liliit ng liliit yung interval. Posible maging napakabagal nung pagliit ng length ng interval. Kasi nga, hindi constant or hindi proportional yung pagbabago. Nakadepende siya dun sa behavior ng function over that interval. Here I forgot pala to include the heading. So this is A, this is B, this is our current estimate C, and then this is B minus A, the length of the current interval. And you see that unlike in the previous experiment, where after 10 iterations, the length of the interval is below 10 to the minus 6. Ngayon, even after 100 iterations, yung length ng interval pa rin ay 0.44574. But luckily, okay, yung nakuha kong estimate for the root ay maganda rin kasi yung function value nung 0.443574 na estimate ko ay 10 to the minus 16 din yung order. So maganda yung estimate ko nakuha, yun nga lang hindi ko nami-meet yung pagliit ng interval. And that will be the case for some functions, especially if there are huge oscillations or if your function is concave downward or convex downward. So yun yung magiging problema natin dito. So hindi kasi lumiliit, hindi guaranteed yung rate ng pag-extend ng interval para sa Regula Falsi Method. That's why in the Regula Falsi Method, it is more preferred to use a function value-based stopping criterion or even a jump-based stopping criterion. Kasi nga, hindi natin nakokontrol yung pag-extend ng interval. We might still have a very large interval, okay? Pero yung root posibleng malapit na siya dun sa actual root o yung estimate natin ay malapit na dun sa actual root. Alright? Kasi hindi random o hindi arbitrary yung pagpili natin ng estimate ng root. Siya ay root ng linear approximation doon sa curve or doon sa function natin. Okay? So again, if you will be implementing it in your research, it might be better to use a function value-based or a jump-based stopping criterion instead of the interval-based method. Kasi you might be doing more work than what is required. Katulad nito, naka-isang daang iterations na ako. Supposedly, tutuloy ko pa yan kasi hindi ko pa nami-meet yung 10 to the minus 6 na stopping criterion for an interval-based method. All right? So, baka abutin ako dito ng hundreds of thousands of iterations. Pero, yeah. Okay. And then, yeah. Ito yung illustration kung kailan hindi ganun kaganda yung performance ng Regula Falsi. Kapag convex downward yung function, makikita nyo napakaliit ng pag-ikse nung current interval na kinoconsider. So this is our original interval. After the first iteration, ito yung haba niya. Tapos susunod, ito yung haba niya. Tapos susunod, ito yung haba ng interval. So parang at every step of the way, paliit na lang ng paliit yung nababawas dun sa length ng interval. That's why even if we are getting closer and closer to the root, alright, hindi naman umiikse ng umiikse yung interval. That's why it is almost discouraged to use the interval-based stopping criterion for the Regula Falsi method. Okay? And then that also happens if there is a very steep change in the function value. Nakita nyo, hindi ganon kaganda yung pagliit talaga ng interval under consideration. And this is actually worse than the previous case kasi aside from mabagal yung pag-ikse ng interval, ang bagal din ng pag-usad ng estimates papunta dun sa actual root. Dito medyo mabilis pa no? Ang bilis nung paglapit dun sa root. Pero if there's a steep change in your in the function value, there's a large fluctuation, okay? Tapos it is this is in the direction of the convergence of your estimates. Masyado pa siyang mabagal bago makarating dito sa actual root. So it might take forever for this method to converge. So that's the thing. Even though we said we are hoping that the Regula Falsi method will accelerate the convergence of our routine compared to the bisection method, hindi siya guaranteed. Ang kagandahan sa bisection method, guaranteed yung mabagal na convergence. Okay? So kahit ano pang function yung i-feed mo sa bisection method, pare-parehas yung bilis ng convergence. Sa Regula Falsi, may mga cases na mas mabilis siya sa bisection method. Pero may mga beses din na mas mabagal siya sa bisection method. So the analysis for the Regula Falsi method should be done case to case. So depende dun sa function mong kino-consider. Okay? So any questions with the bisection method? With the Regula Falsi method? Good question, Charles. Ano yung takeaway ng Regula Falsi than the bisection method? Yung Regula Falsi, mas mabilis siya for most functions, except those that are convex downward or that has steep oscillations or fast rate of growth or decay. Okay? So generally, mas mabilis yung Regula Falsi. Pero hindi siya matatalo siya ni bisection kapag convex downward yung function o kaya may steep oscillations. Okay? So pero kung kita mo naman sa graph ng function, kasi may power naman tayo to sketch the graph of the function, makikita mo naman na hindi naman siya convex downward or wala namang steep oscillations, then mas mabilis yung Regula Falsi. You choose Regula Falsi over the bisection method. Okay? Other questions? Oh, nice question from Chazal. Linear bang order of convergence ng Regula Falsi? Unfortunately, it will depend on the input function. Okay, hindi katulad ng bisection na alam natin na always linear yung convergence. Sa Regula Falsi, yung rate at saka order ng convergence ay nakadepende dun sa function. Okay? Kasi yung pag-compute natin ng value ni C, nung estimates natin, nakadepende siya dun sa functions. Pero remember sa bisection method, yung pagko-compute natin ng C, walang pakialam kung ano yung function, right? So it's just A plus B over 2. It doesn't matter how the function looks like. Kaya nagawa natin yung convergence analysis sa bisection. So Regula Falsi, hindi natin yun kayang gawin. All right? Unfortunately. So jumping from Chasel's question, hindi nga natin siya kayang i-analyze as a whole, all right? Yung convergence ng Regula Falsi. But we can modify the Regula Falsi method a little bit so that we can obtain a rate of convergence that is faster than the bisection method. Okay? So yun yung titingnan natin na next cases, which are modifications of the Regula Falsi method. Okay. Now, itong modifications ng Regula Falsi method ay simple lang naman. Okay? Medyo binago lang natin ng konti yung pagko-compute ng value ni C. All right? So we will consider two possible modifications of the Regula Falsi, and this will allow us to compute for the order of convergence or the rate of convergence of the Regula Falsi method, and to guarantee that it will have a faster convergence than the bisection method. So in general, yung Regula Falsi ay hindi natin masasabi na laging mas mabilis kaysa kay bisection. Pero modifications of the Regula Falsi can be proven or can be shown to be faster than the bisection method. Okay? So tingnan natin, paano natin pwedeng i-modify yung Regula Falsi method. The first one is the Illinois algorithm. Now, ito yung pinagkaiba niya. So kunwari, meron akong function dito. Hindi ko na i-drawing yung XY axis. Sige na nga, drawing ko na nga. Ang gulo yan. No? Hindi na daw i-drawing, pero i-drawing pa. Okay. Diba, ito yung hinahanapan natin ng root. Okay? So it satisfies the requirements of the Regula Falsi method. F of A and F of B have opposite signs. Okay? Tapos yung unang iteration ng Regula Falsi, ganun pa rin, kunin mo yung line passing through paano ko ba ikukwento? Alright. So di ba sa Regula Falsi method, ino-consider natin yung line passing through F of A and F of B. Tapos yung intercept niya, ito yon, from the Regula Falsi method. Okay. So modified Regula Falsi, if you are on the nth interval, okay? So halimbawa, nandito na ako sa A sub n, saka sa B sub n. Kunwari, si B sub n, siya yung dating C sub n minus 1. Right? So nasa nth iteration ako, meron akong A n, B n. Pero si Bn, siya yung dating C sub n. Remember yung C sub, yung mga estimates natin, sila yung nagiging isa sa mga endpoints. So kunwari si Bn yung previous estimate. Now, ang gagawin ko sa modified Regula Falsi Illinois algorithm, alright? Di ba, ang susunod supposedly ay itong green line. Ito yung susunod na approximate, ito yung makukuha kong C sub n. Ito yung classical Regula Falsi. Pero sa modified Regula Falsi by the Illinois algorithm, hindi ko kukunin yung line passing through F of An at saka F of Bn. Ang gagawin ko, kakalahatiin ko yung function value nung na-retain na endpoint. Si An yung na-retain na endpoint galing sa previous iteration. Ito yung A sub n minus 1. Alright? Siya yung lumang endpoint talaga. Si Bn, na-compute ko lang siya, siya yung dating estimate from the previous iteration. So yung lumang endpoint, yung original endpoint na carry over from the previous iteration, instead of choosing this, all right, na pagsisimula ng line na linear approximation to the pink curve, all right, kukunin ko yung kalahati ng function value niya. Oops, palitan ko yung kulay. Gawin natin red. Ang pangit pala, dapat nandito yung, sorry, ayusin ko yung drawing Lipat ko. Oops. Okay. Ito dapat pala si A sub n minus 1. Hindi siya nabago. Oops. Okay, basta ito yon para magpantay yung function value niya. Alright, hindi pala pantay yung function value. So instead na ito yung line na gagamitin ko, na approximate dun sa curve, kukunin ko yung kalahati ng function value nung na-retain na endpoint. So ito yung 1/2 ng f of A sub n. Tapos siya yung gagamitin ko, siya yung i-connect ko dun sa endpoint, dun sa kabilang endpoint. Ito yung C sub n para sa Illinois modified Regula Falsi. Okay? Or sa Regula Falsi method, Illinois algorithm. RFIA. Okay? So kakalahatiin mo yung function value nung na-retain na endpoint, tapos siya yung gagamitin mo para ma-compute yung line. Right? Tapos pag na-compute mo na, nakuha mo na yung equation ng line, kukomputein mo yung x-intercept ng line. So instead of the line passing through f of an and f of bn, kukunin mo yung line passing through 1/2 f of an at saka f of bn. And we are not violating the condition that the endpoints should have opposite signs, or the function values at the endpoints should have opposite signs. Kasi kung positive yung f of an, kunin mo yung kalahati niya, positive pa rin yun. Opposite sign pa rin yun with the other endpoint. So ang kagandahan nitong Illinois algorithm, okay, ay super linear na yung convergence niya. Its convergence is 1.442. I think that's the golden ratio if I'm not mistaken. So mas mabilis na siya ngayon yung Illinois algorithm kesa sa bisection method for whatever function you are considering. Kasi nga nawawala na yung masyadong steep na pagbabago dun sa function value. Kasi instead na yung function value nung lumang endpoint yung kino-consider mo, kino-consider na natin ay yung kalahati ng function value na yon. So nahihila natin pababa yung isang endpoint ng line na kino-consider natin. Remember, look at this. Parang nabawasan natin yung pagiging steep ng graph. Okay? And you see that there is a very huge leap on the closeness no estimate from the Illinois algorithm compared to the classical Regula Falsi Method. And this answers hopefully Chasel's question na yung kahit yung Regula Falsi hindi siya laging mas mabilis kasi sa bisection, pero yung modified Regula Falsi using the Illinois algorithm ay mas mabilis sa bisection method for whatever function you are considering. And you see how clever the modification was na dun sa examples natin kanina sa convex down sa convex upward. Ang problema natin, ang taas nung nare-retain na endpoint compared dun sa function value dito sa kaliwa. Kaya napakalaki ng slope ng line passing through the endpoints. So ang remedy ni Illinois algorithm, instead na ito yung consider ko sa susunod na iteration, kalahati niya na lang, okay? Tapos ito yung kukunin kong line, hindi siya straight line. Basta, kunwari straight line yan. So dun sa hindi modified, ito yung estimate na nakukuha ko. Dun sa modified using the Illinois algorithm, yun yung nakukuha ko. Alright? Mas mabilis yung paglapit nito dun sa root. And actually, it will obtain a superlinear convergence with rate the golden ratio, 1.442. Okay? Na naka-describe naman dito kung paano nyo kukunin. So, yung endpoint nung graph. So, nagkakaroon ka lang ng 1/2 na factor dun sa function value nung na-retain na endpoint. Okay? So, you'll just need to figure out paano nyo so, meron kayong bisection. Paltan nyo yung computation ng C using equation 2.9. You'll get the classical Regula Falsi Method. Okay? Tapos, para makuha yung Illinois version ng Regula Falsi, modify nyo lang ng konti yung pagko-compute ng kay C. Instead na f of an, dapat may 1/2 na kasama. So, the computation or deriving the formula for Cn is left as an exercise 2.6. So, nakabigay na naman dito. Kunin nyo yung equation ng line passing through these 2 points, alright? But make sure ang namumultiply ng 1/2 ay yung function value nung na-retain na endpoint, okay? So, dun sa if statement nyo na pumipili nung mariretain na endpoint, whether it's A or B, alright? Sino yung ipapartner nyo kay C, yung function value dapat nung na-retain, i-multiply nyo na kagad ng 1/2. Tapos, same computation for its x-intercept. Okay? Is that clear? Sorry, I might need to borrow 5 more minutes after this. If you have a class, you can go and then just watch the last 5 minutes of the meeting. Gusto ko lang tapusin yung pangalawang modification ng Regula Falsi para sure tayo magagawa nyo na yung rest ng exercise 1.1. Ezekiel has a question. Guaranteed ba na kung ano yung na-retain na endpoint at first iteration? Ezekiel, hindi siya guaranteed. So pwede siya mag-back and forth. Okay? Dito sa example na to, lagi itong nare-retain, pero in general, hindi siya palagi. So pwede silang mag-jump back and forth. So posibleng, at this point, si B yung ma-retain, pero sa susunod na Regula Falsi, ang ma-retain naman ay si A. So, you need to be careful with that. Right. Pero ano lang naman yun, pwede nyo siyang dayain dun sa if statement nyo. Meron kang if, di ba? Tapos, check nyo kung si f of a times f of c ay less than 0. If this is the case, then si a ay mariretain. So si a ay i-retain nyo to be a. Tapos si b, gagawin nyo siyang c. Alright? Tapos, kukomputin mo dapat yung function value niya. So dito pa lang, pwede mo nang sabihin na yung sabihin nating y new, gawin nyo ng 1/2 ng f of a. Tapos yung y new, ito yung gagamitin nyo pag-compute ng c. Alright? Kasi gusto mo 1/2 ng function value nung na-retain na endpoint, yung gagamitin mo pagko-compute ng panibagong c. Alright? Now else, ito naman yung case ng f of c times f of b ay less than 0. So si b ay i-retain mo to be b. Tapos si a, gagawin mo siyang c. Tapos ang gawin mong y new ay 1/2 ng f of b. Kasi nga, namumultiply dapat ng 1/2 ay yung function value nung lumang endpoint. Okay? So I hope that gives you an idea paano nyo i-modify yung regular. Of course, meron pa siguro dyan sa loob, pero ito yung isang suggestion para minimal yung modification na gagawin nyo. Okay? Alright, so may isa pang modification ng Regula Falsi Method. Ito naman yung Anderson-Bjork algorithm. Yung Anderson-Bjork algorithm, katulad din siya, or kamukhang-kamukha siya ng Illinois algorithm. That's why it is called an Illinois type modification ng Regula Falsi. Kasi ini-scale niya yung function value nung nare-retain na endpoint. Sa modified Regula Falsi, or dun sa tinatawag na Illinois algorithm, dun sa original Illinois algorithm, ang scaling factor ay laging 1/2. Ngayon sa Anderson-Bjork algorithm, yung scaling factor nyo ay equal na kay m. So kung si a yung na-retain na endpoint, ito yung kukunin nyo na line. Passing through a, f of m times f of a, at saka b, f of b. Now, how do you compute for m? You will compute for m using this formula. If 1 minus the ratio between the function value of the previous estimate and the previous value of b, okay? Tapos pag minus mo siya kay 1, ang sagot ay positive, then that's gonna be your scaling factor. But if this guy is negative, may problema. Pag nag-negative ito, ibig sabihin, malilipat sa kabilang part ng x-axis yung function value. Hindi na magkakaroon ng opposite signs, wala na tayong makukuhang root para dun sa linear approximation. So otherwise, if this is negative, you cannot use it as a scaling factor kasi yun nga, mababiolate yung the opposite signs ng f of a at saka f of b. Alright? So 1/2 na lang yung multiply natin. Okay? So this kind of takes care of the slope. Mas pinabibilis niya. Kung yung 1/2 ay masyadong maliit, pwede pa natin liitan yung scaling factor para mas bumaba pa yung function value nung na-retain na endpoint. So ito yung gagamitin natin na formula. But you need to be careful with it kasi itong Anderson-Bjork algorithm, kailangan niya yung function value nung previous C over yung function value ng previous B. Tapos ito ay nangyayari kapag ang na-retain ay si A. Na-retain si A. Tapos napalitan si BN. Tapos dahil dito ang na-retain ay si A, ito ay pang-multiply natin sa f of A. Ito ay scaling factor para sa f of A. Pero kung pabaligtad yan, halimbawa naman ang bago mong interval ay ganito, c sub n minus 1, comma b sub n minus 1. So ang na-retain ay si b, ibig sabihin kukunin mo yung line passing through an, f of an, and bn, comma, m of f of bn, right, where m is equal to 1/2 otherwise, okay? Tapos ito ay 1 minus f of c sub n minus 1, yung previous value, yung previous estimate, all over f of a sub n minus 1, if this is negative, if this is positive. All right? So Cm, pang multiply dun sa function value nung na-retain na endpoint. So ito, yung current endpoint nyo, na-retain si B. Okay? Na-retain si B. So si f of B yung malalagyan ng M. Pero sa pagko-compute ni M, dapat 1 minus function value dun sa previous estimate all over function value nung hindi na-retain na endpoint. Kasi dito si AN napalitan. Right? Si AN naging C sub n minus 1. So napalitan si A sub n minus 1. Hindi nyo dapat itapon si A sub n minus 1 kasi gagamitin nyo siya pag-compute ng M. So medyo mas tricky yung pag-compute ng multiplier para sa Anderson-Bjork algorithm. Okay? Pero if M is always equal to 1/2, then ito yung Illinois algorithm. So mas sophisticated yung Anderson-Bjork algorithm. And unfortunately, in your laboratory exercise part 2, syempre ang pinagawa ko sa inyo ay Anderson-Bjork at saka classical Regula Falsi. So that will be your unwritten assignment. So simulan nyo na i-program yung Anderson-Bjork algorithm. Tapos, after you do that, you can do items 5 and 6. All right? Dun sa item number 6, kailangan, dito pala sa 5 and 6, gagamitin nyo yung same interval na ginamit nyo sa bisection method. Okay? Kahit may comments kami dun sa interval nyo sa bisection method, yun pa rin yung gamitin nyo para sa Regula Falsi at saka sa Anderson-Bjork Regula Falsi. Okay? Kasi sa number 6, ipapa-compare namin yung tatlo. Okay? Kasi yung may mga function value-based tolerance na 10 to the minus 6. Gusto kong makita kung sino yung mas mabilis. And we have seen here na dapat pinakamabilis yung Anderson-Bjork. But we'll see what will happen. Okay? Now, there is still some remarks that I want to say about this, pero simulan ko na lang siguro siya next time. Sorry, overtime na ako ng 3 minutes. Total of 13 minutes. But do you guys have questions about these algorithms? Medyo tricky yung pag-Anderson-Bjork. Pero yun nga, ang key ay i-keep track nyo yung mga old na A sub n at saka B sub n. Hindi pwedeng basta tinatapon yung previous interval. Kasi yung A sub n minus 1 at saka B sub n minus 1, yung mga endpoints from the previous iteration, ginagamit siya parehas dun sa Anderson-Bjork algorithm. All right? So I think that's it for today. Do you guys have questions? Clarifications? Okay, so if there are none, so thank you guys for coming today. Enjoy the rest of your day, and then let's see each other again on Thursday. On Friday. Bye, everyone.
Thank you po, sir.
Thank you po,
Alright.
sir.
Yes, sir.
Ay, yung mga nag-recite or nagtanong verbally, paki-comment naman yung nicknames nyo on the chat box. Thank you.